In this presentation, we will present binarized neural networks. Training deep neural networks with weights and activation constrained to plus or minus 1. Training, or even just using neural networks, is highly inefficient, and today, deep neural networks almost exclusively run on power-hungry GPUs. It is a great challenge to run deep neural networks on low-powered devices such as mobile phones, as well as speeding up the deep neural networks at runtime. The main computational bottleneck is the multiply accumulator operation, which happens many times in the forward pass and backward pass. Our solution is to binarize the weights and activation to plus or minus 1, thus converting the expensive math operation to cheap logical operations XNOR and population count. The main idea is to treat binarization as noise and harness the network tolerance to noise to relax the hardware demands. We binarize the weights as done in binary connect and replace the nonlinearity function with binarized nonlinearity. Since we used backpropagation, we need to differentiate through the binarization function. To do so, we use the straight-through estimator, which simply passes the gradients as they are while taking into account saturation effects. The rest of the multiplication used for the batch normalization layers and the weight optimization were replaced with bit shift operations. This results with binarized neural networks that require 32 times less memory storage and access. To evaluate the binarized neural network's speedup, we programmed a CUDA kernel, which performed 23 times faster than the baseline kernel and 3.4 times faster than the CU BLAST kernel. Viewing the Horowitz power demands table, we can see that by using only 8-bit additions, we can reduce power consumption by 2 orders of magnitude. Therefore, with 1 bit, we can reduce it even further. Our results were tested on small classification datasets, MNIST, SVHN, and CFAR10. In all the experiments, binarized neural networks achieved comparable results to their 32-bit counterpart. On larger datasets, such as ImageNet, we observed a degradation in performance. However, by using more than 1 bit, we can achieve near state-of-the-art results. Full details can be found in our latest work titled Quantized Neural Networks, Training Neural Networks with Low Precision Weights and Activations, which will be presented in the NIPS 2016 workshop.